My studies point to a bizarre and interesting possibility that we don't live in an objective reality and the entire universe might be just a super advanced virtual reality simulation. My name is Dr. Melvin Vopson. I was born in Bucharest, Romania. So in 2012 I joined the University of Portsmouth as a lecturer. Since 2014 I'm senior lecturer. And so I continue my research essentially in what I call the field of research. I would just to put a label on it, I would say condensed matter physics, solid state physics research. So Shannon developed the information theory in 1940s. He became the father of digital computing, really. He gave the unit of bit. So Landauer realized something very interesting. He realized that in thermodynamics we know there is a principle that any irreversible process has to be dissipative. In other words, if you have something that takes place irreversibly, you should expel some energy in this process, dissipate some energy. So if you could store information in vacuum, let's say, not supported by anything, you will still have an energy associated with this process, irreversible process. So the fact that information at erasure dissipates energy, it means that information is energy. It's like saying mathematics is physicalized. Mathematical states have an energy, if you want. It's a very, very abstract concept. If a bit of information is physical, so it has an energy associated to it which can be detected at erasure, my question was, where is that information going when the bit is at equilibrium and it stores information? That energy can't exist on its own, like it needs to be in some form, okay? One way of maintaining the energy is to condense it into matter. In other words, acquiring mass. And this is linked to Einstein's special relativity and the famous E-mc square relation, energy is mass. My mass energy information equivalence principle, formulated in 2019, states that information is not just a physical form of energy, but is also mass. It has mass. And it can interchange between these states depending on what the state information is in. If it's at equilibrium storing information, that must have a small mass. The bit must have a small mass. If you erase it, that mass gets converted into energy dissipation. And then once you formulate this and you start looking at the physics from this angle and everything, then a number of very interesting possibilities emerge. And I came up with a very interesting concept of matter DNA. It's on the same principle as living organisms. So a living cell contains all the information about itself in itself. All that data is stored in the cell. I was thinking, could it be possible that the matter itself operates in the same way? So maybe there is a DNA of matter that is stored in the matter. And what that would be is the characteristics of elementary particles. What makes an electron an electron? Okay, so an electron is, it has specific characteristics. We know it's an electron because it has a specific charge, a specific spin, it has a specific mass. And an electron here behaves the same as an electron on the moon or an electron in a different galaxy or at the edge of the universe. They are all the same. And the question is, and the proton it has different characteristics and the neutron has different characteristics. Everything is different. So the first question is, how do they know, all these guys, how do they know that those are their characteristics and they behave the same and they're subjected to the same rules and the same properties anywhere in the universe, although they are so distant from each other? And so maybe the elementary particles, the building blocks, the smallest things that we know about that make up everything in the universe, maybe they are stumped with this information about themselves in themselves. And I started to look at how much information we are creating at a planetary scale, how many bits of information, and what does it look like in terms of the mass of this mass energy information equivalence principle, and what does it look in terms of the energy balance? Because you need to consume energy to create information, okay, and to store it. And I came up with something called the information catastrophe. This is 2021 published, I believe, or 2020 published. Every year, we create 10 to the power 21 bits of information, the range, yeah? Our planet has 10 to the power 50 atoms. Everything that makes our planet, from atmosphere to oceans to everything, the biosphere, everything, it's called information catastrophe for a reason, because the growth rate is about 33% year on year. And we are not deleting any of it. A 20% growth rate, we're going to make more bits of information than all atoms on the planet. At 20%, 340 years. We overtake the atoms on the planet with digital bits. At 50%, 150 years. Are we going to reach that point? We can't, because something has to give. You can't, it's just a theoretical endpoint that we are going to hit if we don't do anything. And that is what led me to this simulation hypothesis. If we are making 10 to the power 21 today bits of information, and we've been doing this since 1970s. You look at half a century, okay, of digital technologies, and we already are looking at astronomical numbers, okay? And if all the atoms in the world, on the planet, are just 10 to the power 50, and we are going to reach that number in 150 years at this growth rate or something like that, it makes you wonder. I mean, any normal person will think, could it be that maybe we already are in some kind of digital virtual reality world? Maybe this already happened, because the numbers are just, if you look at the scale, the time scale, like thousands of years or billions of years, okay? What we are doing in decades, okay, in terms of shaping up, you know, these entities, I call these digital entities, the digital states and technologies, is staggering. It's almost incredible. If we are doing this now, how our planet or our society is going to look in 1,000 years? We've been doing this for 50 years. Okay, we invented electricity in 1850 or something. Then it's not far-fetched to assume that an advanced civilization, or maybe ourselves in the future, we reached a technological level where we can simulate our world or the whole universe, and is indistinguishable from the reality. One easy way of testing this would be to physically measure the mass of information. Okay, so you take a device of a given volume of information, you measure that mass, write it down, and then you erase everything and measure it again. If there is a mass change, in other words, a mass reduction, that would be the first proof that information has indeed mass. Maybe we can detect this information hidden in the particles by erasing it. Now, if you take an electron and a positron and let them collide, okay, they will annihilate and dissipate all their mass energy into gamma photons, okay? If they store information in themselves, about themselves, you should expect to see that information also conserved. It cannot disappear, it should be conserved. So all that mass information at erasure should dissipate somehow. I did the calculations, and it should come out as infrared photons at room temperature at around 50 micron wavelength, okay? All you need to do is to do exactly what they are doing at the moment in terms of positron electron annihilation, but add a few more detectors there, specifically infrared detectors. The second signature is, if you change the temperature of your environment, you should change the mass of the information bits in the particles. You should change, so the infrared information photons should scale with the temperature of the sample. So let's assume you detect them. The absolute confirmation is by changing the temperature of the sample and seeing the shift in the wavelength of these infrared information photons when detected. If you notice that as well, it's total confirmation of this, and it's a true eureka moment. So this is, in a nutshell, the experiment. Popular science articles that appeared, they talk about the simulation hypothesis and the world being, universe being a simulation, and this experiment may be proving that. But in fact, it doesn't prove entirely that. It underpins that concept through empirical evidence, but it doesn't mean necessarily that is totally the consensus is that that is what is happening, is one possibility. It's also wrong to assume that a negative experiment indicates that the theory is wrong. It means look more into this because we are onto something. But a positive experiment is a groundbreaking piece of research. It will force us to look back at the physics from this new angle and everything in it. It means that we missed an important component in everything, in all the physical processes and matter and everything, is the information component. It will revolutionize many things. It will bring changes in quantum mechanics, but the beauty is that it doesn't contradict anything. It's only complementary. It doesn't say special relativity is wrong or I don't know, thermodynamics is wrong. No, it doesn't contradict absolutely nothing. It's not exclusive, it's complementary to everything we do. It means we have additional tools to explain things that we overlooked in the past. This information, DNA of matter, and this information component that is in everything, in the fabric of the universe, potentially in the space-time itself, it needs to be looked at. So it's a big game changer, it's a big thing, yes. If you are excited about uncovering one of the greatest mysteries in the universe, please support our experimental efforts by going to www.informationphysicsinstitute.org. Thank you very much.